Welcome to Matematika. Today we're going to do the rational functions and end behavior. So we'll start with the end behavior of rational functions. A rational function is a function which can be expressed as a quotient of two polynomial with a non-zero denominator. Like the denominator should be not equal to 0. For example, you are given an f of x is equals to g of x over h of x, where g of x and h of x are polynomials. So the h of x, which is the denominator, should not be equal to 0. That is the what the definition of the rational function says. So an example to that, you can have f of x equals 1 over x. F of x equals x plus 1 over x squared. And f of x is 2x to the fourth over x cubed plus 3. These are the examples of a rational function. Let's go to the end behavior of a rational function is determined by comparing the degrees of these polynomials that is in the rational function. So the polynomial with the higher degree has a greater effect on the end behavior of the function. Let's follow this by looking at the three cases that arise when analyzing the quotient of the leading term of a rational function. So, a rational function is in the form, this is in the form of f of x equals to ax to the power of m plus whatever other terms would that be over b of x to the power of n plus whatever other terms would that be. So let's do this. In case 1, the degree of numerator is greater than the degree of the denominator. Like, okay, this is the degree of numerator and this is the degree of the denominator. That means it says in case number 1, if the degree of numerator, which is m, is greater than the degree of denominator, which is n. So what's gonna happen? Find the quotient of the leading term. That's the result will be a polynomial. So the end behavior of the polynomial is the same as the end behavior of a rational function. If the polynomial is linear, then the rational function has a slant asymptote. So if you remember the term asymptote, it says parallel to the linear polynomial. Remember in Algebra 2 what the asymptote means? We have that. Asymptote is a line, right? A line that continuously approaches a curve but does not meet if any of the limited or the whatever distance would that be. So sometimes we call the asymptote as the tangent. It just touch the curve but not intersecting the curve. So here, this is the asymptote. Okay? And for m greater than n, the asymptote is a slant asymptote. Okay? It just touch touch the curve but not intersecting the curve right here. Just pass through. Here, just pass through. Okay. So in this example, let's say you are given like here r of x is 4x to the third power plus 1 over 2x squared. So you see the numerator is greater than the denominator, the degree. So the degree of numerator is 3 is greater than the degree of the denominator. If this happens, the limit, okay, as x approaches to positive infinity, this is the positive infinity right here, and this is the negative infinity, the function would be either it goes to the positive or the negative. We'll determine that later on. So goes to either positive or a negative infinity, and the limit as x approaches to negative infinity, the function still would be a positive or a negative infinity, depending on the situation of what is given in the problem and what kind of curve do we have. Okay, case number 2. In case number 2, the degree of the numerator is equal to the degree of the denominator. That means the degree of numerator is equals to the degree of the denominator. Okay. Find the quotient of the leading coefficient. The result will be the constant value, b. And there is a horizontal asymptote at b. The ends of the rational function will approach the asymptote. Okay. So like this, for example, you are given the, okay, I'm going to use it here. You are given the r of x equals, I'm gonna make this big, 6x to the 5th power plus 3 over 9x to the 5th power plus x cubed minus x. Okay, let's look at the degree. Our degree in numerator is 5 and in denominator is 5. That means 5 is equals to 5. M is equals to n. When that happens, you have an asymptote. Okay, so let's look for that asymptote by getting the coefficient of the numerator. So our leading term here is 6x to the 5th, and the denominator is 6x to the 5th. When we cancel that out, our leading term would be 6 over 9, and that will be our y. Okay, 6 over 9. So we can reduce that by 3, but that would be 2. By 3, that would be 3. 2/3. Alright, so in other words, our limit in this case, our end behavior in this case, as it approaches to positive infinity, the function of x would be equals to, this is a and this is b, would be equals to a over b, which is in this case we have 2 over 3. A is the coefficient, okay, a is the coefficient of numerator, and b is the coefficient of the denominator. That's why we say a over b. Well, in limit of x approaches a negative infinity, still the function still equals to a over b, which is 2 over 3. If we look at this, where is our asymptote here? Asymptote is right here. It just touched the line. Okay, this is the asymptote. All right, where is that located? The y equals 2 over 3. That means when you divide that, that is 0.66 something, less than 1. And that is the location of the function f of x. All right, case number 3. In case 3, we have the degree of the numerator is less than the denominator. Degree of the denominator. So in other words, m is less than n. That's the degree. There is a horizontal asymptote at y equals 0. So if we look at this right here, the line just touches the curve at y equals 0. The ends of the rational function will approach to this asymptote. So this is the positive infinity and this is a negative infinity. So in other words, it says it's y equals 0 as the horizontal asymptote. So you indicate that the horizontal asymptote there is equals to 0, or at y equals 0. So what would be our limit notation there? As x approaches positive infinity, the function is equals to 0. As it goes on and on and on, like if you apply in the equation, so if we look at our given here, we have r x is 4x squared plus 5 over x to the 4th. See, the degree is less than the degree of the denominator. Degree of numerator is less than the degree of the denominator. That means as we keep on plugging in any number that is greater than 0 to the right, as it approaches to a positive infinity until it will get a 0. So the limit as x approaches negative infinity, the function of x is equals to 0. So these are the 3 cases of rational functions and behavior. So let's follow that 3 cases and then find out of some of examples here. Let's do example 1. Determine the end behavior of the given rational function. End behavior. Okay. F of x equals x minus 5, then over 2x plus 3. Alright. So look at the degree of numerator and the denominator. So m equals n. They're equal, first degree. Alright. So that means, what case is that when they are equal? Case 2. Okay, I'll go back to here. In case 2, they are equal. Do we have an asymptote here? The asymptote is the ratio of the coefficient of the numerator well, over the coefficient of the denominator for case number 2. So in our numerator is 1 over x. See that if it's x, the coefficient there is 1. Denominator is 2x. That means y is equals to 1/2. That's our horizontal asymptote. Okay? This is the horizontal asymptote. So we could say that the limit as x approaches positive infinity, the function of x is equals to 1/2. As well as the limit as x approaches negative infinity, the function of x is equals to 1/2. All right, let's do number 2. 2x squared plus, 2x plus 1 over x squared. So the numerator is less than the denominator, the degree. So 1, that's less than. So what case would that be when it's less than? It's case number 3, right? So what happened in case number 3? What will be, is there a horizontal asymptote? The horizontal asymptote is 0. That's the y equals 0. What does it mean? It means that there is a horizontal asymptote when y equals 0. That's what happened. That's like in this case right here. Right? Okay. Let's do the limit, the end behavior. So in this case, the limit when x approaches positive infinity, the function of x is equals to 0. When the limit when x approaches a negative infinity, the function of x is 0 because of this horizontal asymptote. So as we move on and on to the positive and to the negative side, whatever it is, how far it goes until it approaches to 0, until it will become 0. Let's do number 3. Function of x is 2x squared plus 6x minus 3 over x minus 9. Let's look at the degree. So the first thing you have to look at is the degree. That means the degree of numerator is greater than the denominator. That is x right there. So this is case number 1. You have a slant asymptote in this case. Maybe we're going to graph this, but quietly sure you have no horizontal asymptote. Look at the cases. So when it's case number 1, you have no asymptote here. Okay. So the limit x approaches positive infinity, the limit might be approaching, sorry for that, approaching a positive or negative infinity. We'll see that when we see a graph, then we'll know. Function of x might be approaching as well positive and negative infinity right there. In number 4, f of x is 12x squared plus x minus 2 over 2x squared minus 8x minus 2. Looking at the degree, m equals n. The degree are equal. That is case number 2. When m equals n, so what happened to our horizontal asymptote there when they are equal? Right? Horizontal asymptote would be equal to a over b. We call that the coefficient of the numerator and the coefficient of the denominator. So when we look at the first term, 12x squared over 2x squared, we cancel up. We have 12 over 2, that is equals to 6. That's our horizontal asymptote. So that means when y is equals to 6. So writing down the limit as x approaches positive infinity, our f of x would be equals to 6. The limit as x approaches a negative infinity, the f of x is equals to 6 as well. For number 5, okay, f of x is equals to x to the 5th over x cubed minus 2x squared plus 1. So greater, m is greater than n. So do we have, what case would that be when it's greater? What case do we have? Case number 1. Okay, when m is greater. So do we have a horizontal asymptote here? We have no horizontal asymptote. So maybe it will be into a positive or a negative infinity in this case. So we have the limit as x approaches positive infinity. Our f of x here would be a positive infinity. The limit as x approaches to negative infinity, our f of x here would be negative infinity. Since there is no asymptote. Okay, let's look at this graph. Using the graph. Using the graph right there. Let's look at what we can say is look for the asymptote. Is there an asymptote that is, I think if I can see a broken line here. I will trace it. It passes at when y as 4. So we could see a horizontal asymptote there. Y equals 4. All right. We can use we cannot use this vertical asymptote right there. We can use this when we find the domain. But in this case, we only need the horizontal asymptote. Okay, this is the horizontal asymptote. I just use an a horizontal asymptote. So the limit as x approaches positive infinity, the function is equals to 4. The limit when x approaches a negative infinity, the function of x is equals to 4. Let's do graph 7. Do we? No, we cannot have because we cannot have a horizontal asymptote here, because if we try to draw a line on the x equals 0, it intersect at this point. Asymptote just touch and not intersecting the curve. So in this case, in number 7, we have no asymptote. All right. So that means the limit would be a positive or a negative infinity. So if we look at here, positive infinity, and here a negative infinity. All right. So in this case, the limit when x approaches a negative infinity, look at the end of the curve here. It goes up. So it approached to a positive infinity. Well, the limit when x approaches positive infinity, look at the curve. Okay. It approaches to a positive infinity. Let's look at number 8. Okay, we have an asymptote there when y equals 0. That is the horizontal asymptote. So in other words, we could say that the limit when x approaches a negative infinity as we go on and on and on, if we try to plug in any values, the function until it reaches into 0. We can use, when you have a calculator, you can use the calculator by doing that. And the limit as x approaches to positive infinity, what it means here, as it approaches to negative infinity, when we plug in a very small value, as we keep on putting in a very small value, the function would, until it approach to 0. Same thing what happened to the positive infinity, until you keep on putting in a bigger value, then until it gets into 0. That's why the function is equals to 0 in this case. Okay. Letter B. State the domain of the following. You have x to the first power over 2x plus 5. Okay. What does it say in the rational? Because you are asked the domain, so we are focused on looking at the x line, the x-axis, the numbers that are in the domain, and that is in the x line. So if you remember on the definition of a rational function in such a way that the denominator should not be equal to 0. So let's look at the denominator, 2x plus 5. This should not be equal to 0. So how are we going to do that? 2x equals 5. Let's get that value of x, that the value should not be equals to 0. That's 5 over 2. That means the x should not be equal to 5 over 2. If we look at in our number line, this is x and this is 0. 5 over 2 is somewhere on, this is negative. So 1, 2, 2 point something. Let's say this is negative 5 over 2 located. So to the left, that's negative infinity. To the right, That's positive infinity. So how are we going to write our domain here? From interval negative infinity to negative 5 over 2, and from negative 5 over 2 to positive infinity, excluding 5 over 2. Because if you plug in 5 over 2 to the function, then the denominator would be equal to 0. When the denominator would be equal to 0, then that's not define the rational function. Okay, let's have number 2. F of x is x squared plus x squared minus 4 over x plus 3 times x minus 7. So we'll not make the x plus 3 and x minus 7 should not be equal to 0. So x plus 3 should not be equal to 0. X should not be equal to negative 3. X minus 7. So x should not be equal to 7. Let's look at that for the domain. 7 is right here and negative 3 is right here. This is the negative infinity. This is the positive infinity. So we have 3 parts here. This portion right here and what is happening between negative 3 and 7, you can plug in any number besides negative 3 and 7, because if you do negative 3 and 7 to the function, the denominator would become 0. And from 7, interval from 7 to positive infinity. So our domain would be from between negative infinity to negative 3, and the interval from negative 3, negative 7, and the interval from 7 to positive infinity. That is the domain. Okay, for number 3, we have x cubed plus 7x squared plus 12x over x squared plus 2x minus 15. Let's focus on the denominator. We can factor this out by 15, by 5, and by 3. Okay, so we are not making x plus 5, x minus 3 should not be equal to 0. So x plus 5, x should not be equal to negative 5. X minus 3, x should not be equal to positive 3. So this is 3, this is negative 5, that's 0, and this is 3. So we have still positive infinity, negative infinity right here. We have 3 parts for our domain. Okay? The interval from negative infinity to negative 5, but negative 5 is excluded. And between negative 5 and 3, 3 also is not included. And 3 to positive infinity. 3 is also excluded, because if you plug in negative 5 and 3 to the function, the denominator would become 0. Okay. We'll find the end behavior. The domain in this case, Okay. So we don't need to look for the asymptotes here because we are focused on the domain. So we draw a vertical line right there towards the graph so that we know the interval along the x-axis right there. So we can see at this point and this point right there. That's negative 1 and this is 1, right? And this is towards the positive infinity and this is the negative infinity. So what would be our domain? All these values right here can be plugged in to the function, but except negative 1 and 1, because when you plug that in, uh, the denominator of the function would become 0. So we have a negative infinity interval to negative 1, and we have a negative 1 between negative 1 and 1, and we have from 1 to positive infinity. Okay, this is the interval between them, but not negative 1 and 1. That should be a no case to that. Okay, let's do this. Where can we? Okay, we can have this as an asymptote. The x value. There is no other x value. We cannot do x here. We cannot do x here because it crosses the graph. The asymptote should not cross. It's just a line that is about approaching to the chord but not touching to the chord. So our domain would be, this is the positive infinity and negative infinity. So we have the interval from negative infinity, this is negative 2, right? So to negative 2, and from negative 2 to positive infinity. Okay, that's it. I will do more on problems and solutions on rational functions and end behavior on my next video. Okay, what I can say is that if I can do it, so can you. Don't forget to hit the like button and subscribe if you haven't subscribed. Thank you and see you on my next video.